Hello everyone, and in this lab, titled Lab A, Memory Forensics Analysis and Detecting Process Injection Using Volatility. My name is Kamei Ige, and just to tell you about the tool that we'll be using, which is an advanced memory forensics framework titled Volatility. It can help determine whether malware was infected on a machine, and to support this with evidence such as network artifacts and the like. In this scenario, APT416 was able to victimize their target using a spear phishing attachment, and by abusing Microsoft Office's functionality of the Dynamic Data Exchange Protocol, which is an inter-process communication system that allows programs to alter objects provided by other programs. In this scenario, the attacker created a payload for the victim and received a shell when the victim opened the attachment. They did this through Metasploit. And as you can see here, when the victim did open, the payload was executed and they got an interpreter shell. The attacker noticed that this was a low level user, in other words, a local user, by getting the UID and retrieving some of the system info. When viewed, the payload is actually using DDE Auto to leverage Reg SVR32 to register a DLL called scrobj.dll, which is famously known for a UAC bypass technique. From here, the victim decides to get a process listing, and due to the nature of the low privilege user they exploited, they decided to target taskhost.exe, which is always started by services.exe in Windows. Process ID of services.exe, and here's the parent process ID of taskhost, which is indeed services. From there, they migrate. Now, process migration Metasploit works as such. You get the PID, you check the architecture of the machine, check if the interpreter has the cdebug privilege, and it calls a bunch of API functions. Now, let's move on to the defensive analysis with volatility. A generalized rule when performing memory forensics is to grasp an understanding of the parent-child relationships on the operating system. For this, Volatility has a plugin called PS-Tree. Now from here, when we look in the PS-Tree, if we are to examine the timings of the processes from the top, we notice that there are some processes that could raise suspicion. For example, we see that the processes that were started from PID08, which is services.exe, have a start time of 1706 UTC with some slight deviations. Here are all the processes with the parent process ID 508 and the start time, which is 1706. But again, there are some deviations, such as taskhost.exe, which is a Windows process that is designed to alert users when closing dialog boxes. Now, taskhost.exe does look like maybe it could be a suspicious process, which can be looked into to see if there are any suspicions with it. And the reason why we want to look at this is because it should have a start time of its parent upon boot up, but the time differences do not align. So we should also look for network artifacts so that we can observe any TCP endpoints, TCP listeners, UDP endpoints, and even UDP listeners. We can use a NetScan plugin with Volatility to observe such scenarios. Scrolling along, to the naked eye, maybe we might not see anything of suspicious here. But one thing I did notice after observing for network artifacts is that there was a partial instance that was created between a foreign address with port 4444. A quick Google search on port 4444 shows some interesting results. This port has been known to be associated with some malware, such as the Blastoworm and Radon. So we can ascertain that this port has been used for nefarious activity, for now. However, we'll shift our focus on examining now PID 3488, which was a partial executable. Now let's examine the PEB structure of our suspected malicious PowerShell. We can do this by examining the loaded modules, including the executable's base address. We can then examine this by using a loaded module with volatility called DLL list and LDR modules. And we can see here by doing so, we don't find anything that could be of useful. And this is because of the exit time of the executable. However, we need to be sure if it was malicious or not. So let's examine the supposed malicious PowerShell.exe executable PID3488 by using Volatility's memdump. Memdump extracts all memory resident pages of the process into a DMP file. And then we can examine by looking at the strings. Now, one thing we should be careful of when we examine the strings is because of the size of the memory, a lot of output was uh, outputted into the terminal. So by examining this on my own end, I did notice that this PowerShell executable performs some form of DDE auto to leverage the regsvr utility at this address, this foreign address, and the scrobj.dll. So this does seem to be peculiar because now we can be somewhat sure that DDE auto was used for macro execution, and it seems like it was used to leverage the regsvr32 binary and register the scrobj.dll. Again, a quick Google search will definitely give you more information on this, as it was introduced and first made public by an individual by the name of Casey Smith. So because of the fact that the executable is also associated with MS Word, we can ascertain that the victim opened up a Word document that was malicious, as it contained macro code via DDE auto for the attacker to bypass UAC and gain some form of shell or access. However, that doesn't help us with taskhost.exe, so let's jump back into PID 1844. Let's investigate the VAD structure of the executable. VAD stands for Virtual Address Descriptor, and it is a computing term to gather information within an address space of a specified process. Volatility provides 3 plugins for this: VADtree, VADinfo, and VADdump. In this case, we'll use VADinfo to enumerate for the taskhost.exe executable, and we notice some interesting findings over here. The permissions, as you can tell by the protection, is page, execute, read, write for these 4 VAD nodes. And as you can see here, the start address and the ending of it, of these 4 VAD nodes. These are some anomalies which can be used to detect code injection. For example, the 4 VAD nodes above have a protection, like I was saying, a page, execute, read, write. However, taskhost.exe, when normally loaded, would have a protection permission of page, execute, write, copy. This is a red flag, as it can indicate that some form of code injection was done on this executable. To emphasize this further, we'll use Volatility's malfind plugin. This plugin with Volatility will help us find hidden or injected code based on permissions, such as the VAD tag and the page permissions. Looking in, we see here there are some MZ injected headers. These MZ's headers signify possibility of a PE code injection within our executable. So what we'll do is we'll dump the memory regions of that process and upload them to VirusTotal to see if any AV engines detected it as malicious. And as you can see here, the 4 VAD nodes, when dumped, were proven malicious. So based on the memory forensic analysis, we can ascertain the following timeline. The attacker sent a victim a malicious Word document that allowed macro execution for UAC bypass. When they obtained an interpreter shell, they then migrated into taskhost.exe for persistence. So I just want to let you know that Volatility is a great tool. Thank you for watching. And we'll elaborate this further to look into how Volatility can also detect a malware technique known as process hollow.